Hello everyone. In this video, let's learn how we can design a D flip-flop circuit and truth table. And let's see the difference between rising edge D flip-flop and falling edge D flip-flop. In the previous video, we saw the SR flip-flop. And then also we saw the truth table for it. So now let's take this SR flip-flop and modify it to make it D flip-flop. So actually this is very simple. So we can take the SR flip-flop shown to the right. It has two inputs, S and R. And we have the clock. And also we have the outputs Q and Q bar. So to make it a D flip-flop, we can simply add an inverter at the reset and then tie it to the S. So this will be our S. So and then this input now become our D input. Let me put S and R inside so we eliminate the confusion. This is S and this is R. And this is our clock. Now the symbol for the D flip-flop becomes as follows. So we can have the rising edge here. So we have this blocks, we have D input, we have the clock, and for rising edge, we can just have a little triangle inside. And then we have the Q and a Q bar output. So this one is rising edge, D flip-flop symbol. And then also we can have here the falling edge. So we have the D input, we have a clock, but we can add a little bubble here and then triangle inside. So this is our clock. And then we have two outputs, Q and Q bar. So this is the falling edge symbol. Now let's obtain the truth table. So the truth table for D flip-flop is very simple. So we have D input, so we have the input D, we have the current state of the system, and we want to obtain the next state Q plus. So when D is disabled and the current state is 0, so what will be the next state? So looking at our circuit here, D is 0, that means S is 0, and R, because it's going to invert the 0, R is 1. So let's write it here. For D equals 0, we have S is 0 and R is 1. So let's look in the truth table for the SRD flip-flop. So that's what this will give us. S is 0 and R is 1. We're looking in this row here. So we reset the Q to 0. So that means the next state will be 0. Now let's see when D is 0, but the current state of the system is 1 instead of 0. We will end up with the same S0 and R1, and also we will reset the state to 0. So if it's 1, we will reset it to 0. Also this row, the next state will be 0. Now let's see when D is 1 and the current state is 0. So D is 1, that means S is 1, and R, it will be the inverter of 1, it will be 0. So let's write it here. When D is 1, that means S is 1 and R is 0. So let's look in the truth table for the SR flip-flop. So when S is 1 and R is 0, we're looking in this second row here. So we set the Q to 1. So that means the next state will be 1. And similarly, when D is 1 and the current state is 0, we still set the next state to 1. So very beneficial observation here, looking in D and Q, they are equal. So in D flip-flop, the characteristic equation will be D equal Q plus. So let's take the following timing diagram and try to plot the Q state on it to better understand how D flip-flop works. So let's do this as a falling edge D flip-flop. So falling edge trigger. So first we need to look at the clock signal and identify all the falling edge locations. So as we saw in the previous video, falling edge on the clock is whenever the clock goes from 1 to 0. So in this area here, it's going from 1 to 0. In this area here, it's going from 1 to 0. In this area here, we have falling edge, falling edge, falling edge, and falling edge here. So let's complete the dashed line. So we know this is the falling edge location. Now let's plot the Q state. So let's assume Q starts at 0. So that's Q starting at 0. So the first edge trigger, we will have state change. So let's look at D in this location. So D at this falling edge trigger is 1. So that means since D equal to Q plus, so the next state will go to 1. So here we will have, sometimes you see a delay, so it go to 1. And then it remain 1 until the next edge trigger. So in this edge trigger, what we have D is 0. So that means the next state will go to 0. So now we will go to 0 and then remain 0 until the next edge trigger. And this edge trigger, looking at D, it's 1. So that means we will go to 1 and then stay 1 until the next edge trigger. At this edge trigger, D is 1. So that means we stay 1 until the next edge trigger. And this location, obviously D is 0. So that means we will go to 0 until the next edge trigger, falling edge trigger. And this location, D is 0. So that means the next state will remain 0 until the next edge trigger. Now let's do the same thing, but for rising edge trigger. So let's use another color for this. Let's use red color. So here we have a rising edge. Here we have rising edge, rising edge, rising edge, rising edge, rising edge. So in red, we're assuming we want to plot Q for rising edge trigger. So let's do it. Let's first draw the dashed lines in this location on all the rising edge. Let's assume also Q starts at 0. So we start at 0. At this rising edge trigger, obviously D is 1. So that means we go from 0 to 1 until the next rising edge trigger. And this rising edge trigger, D is 0. So that means we're going to go to 0. The state will go to 0. Remain 0 until the next edge trigger, D is 1. So that means it will go to 1 until the next rising edge trigger. And this location, D is still 1. So that means the next state will remain 1 until the next rising edge trigger. And this location, D is 0. So we will go to 0 until the next rising edge trigger. In this area, D goes to 0. So that means we will remain 0 until the next rising edge trigger. So that's it. Q in red, we assumed we did as if it's rising edge trigger, and in the blue we did as if it's falling edge trigger. I hope this was helpful on the D latch. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.